Yesterday, we did a discussion on the subject of bit shifting, shift registers. And keep in mind that there's no such thing as a shift register. We call it a shift register because we're going to use that register as a target to shift the bits in. I spent more time pontificating than I meant to, so I basically got through bit shift left and didn't even get started with bit shift right, which is actually a little bit more complex because bit shift left, you're always pushing in the bit address value into bit 0, the least significant bit, and then you're shifting a length of bits to the left. And they unload when they leave the last position into the unload variable, whatever you named it. In our case, we named it output 0 so we could see a light come on when it unloaded to 1. Keep in mind, if it unloads a 0, it turns the light off. If you unload 2 zeros in a row, it's turned off 2 times in a row. Well, how can you tell the difference between turn it off once and turn it off twice? You can't. So the ones are the only things that you can really observe moving. I guess if you put in all ones and then injected a 0, you can see the 0 moving. So you would see the unload light stays on all the time and then goes off when a 0 gets unloaded. Okay, today we're going to do bit shift right. With bit shift right, instead of loading the bit address at the least significant bit, bit 0, you load it at the end of the length and then it goes back to the right towards bit 0 and it unloads in at bit 0. So it's a little bit more complex in how you look at it. So let's jump in there and do the bit shift right. We're not going to labor with this diagram like we did for the bit shift left. And you notice what's changed is we have our push cylinder over on the left end instead of the right end. So when it extends, it pushes the ping pong balls to the right instead of the left. We're working with a length of 8 bits. And these 8 bits can be anywhere in between sequence bits array 1 and 100, meaning that it could be 1 through 8, or it could be 100, 99, 98, 97, and so forth. It could be the first 8, the last 8, or any 8 in between. Now, the unload address is actually in 2 locations. There's an unload bit that retains whatever pops out of position 1 there into the unload address. And then if you've assigned a memory location to the unload function, then not only is that the state of that bit going to reside in the unload position, it's also going to reside in the memory location that you specified. You'll see that when I start showing you in the lab project. So the length can be anywhere in between the first and last element of your array. However, if you have a offset of 0, then it will be the 8 bits closest to the least significant bit, which means it would be sequence bits element 1 through 8. If you have a 0 offset, if you have an offset of 2, then it's going to start with sequence bits 3, element 3, and then take that and then the next 7 bits. So you'll see that in the lab. And as you would expect, the bit address, which in this case is input 4, it basically has a black ping pong ball or a value of 1 staged up. So remember the yellow square with a black ping pong ball in it, or it could be a white one in there, a 0. It's not part of the length, it's not part of the array sequence bits. It's input 04, literally input 04. And then input 02 is the execute. So if we execute by turning on input 02, it's going to take the value of input 04 and put it into 8. But to do that, first it has to shift position 1 out into the unload. 2 to 1, 3 to 2, 4 to 3, 5 to 4, 6 to 5, 7 to 6, and 8 to 7. Then it pushes in that black ping pong ball. Now, because we're using ping pong balls, you could just say it all happens at once. But literally, in the firmware or in the executable, it is going to copy 8 through 2 to 7 through 1, and then replace 8 with whatever the state is of input 04. Now, the only thing that really doesn't work out in this diagram, and I suppose I could have redrawn it once I realized this, is that this does not change the value of input 4. So you're not removing the value of 4 and pushing it into the leftmost element of the array that represents the length 1 through 8. You're not removing it from input 4 and putting it into element 8. You're copying it from input 4 into element 8. Now let's look at the actual lab project, and the lab project I'm going to show you is different than the one in the manual. Remember, if I can find a way to do something different in my lectures without skipping the subject, in other words, if I can enhance it, change something, it just enriches the learning experience. So let's look at the lab project. Here's a bit shift right instruction for the Micro 800 controllers. And if you look at the left edge, you'll see 5 indicators of some function. And on the right side, you'll see 4. On the left side, you see execute source, source offset, bit address, and length. On the right side, you see done, unload, error, and error ID. Obviously, if there's an error, that's going to go true. If there's no error, it'll be false. If there is an error, then there should be an error ID that pops in there. We're not going to pursue errors. Now, unload is kind of interesting. Part of the data structure for this BSR. BSR1 is the memory location. So let's go to global variables. I can't remember if I put it in global or local. So it must be in local. There it is. So if I expand that, and by the way, you'll notice this is the new version 13 variable grid, as they call it. It's the exact same data, it's just a different look to it. These are all of the, I guess you could say, components of a BSR instruction. You got to execute source, source offset, bit address, length, done, unload, error, and error ID. The point I wanted to make is there is an actual bit location. Remember that BSR underscore 1 is an instance of the BSR data type. So this is the BSR data type here. This is what it's made up of. It's a BSR data type. That's what it says right there. And then again, the unload, that is an actual bit in memory. So you can address BSR underscore 1 dot unload. So when you unload a bit from the register that you're shifting the bits in, it leaves that register, but it resides in the unload bit. And if you have an address attached to the unload bit, it resides there too. Well, enough for this. Let's go back to our logic. I created an unsigned integer called offset and an unsigned integer called length. That way I can change them on the fly. Normally people would just put a 0 in here and an 8 in here. What I did was created variables. Here's offset and length, and I put in initial value of 0 and 8. Doesn't have to, it could be 0 and 0, and then you could put in an 8. The reason I do this is because when I download with the data. That way it always downloads a 0 and an 8. This would be a 0 anyway when you download and you don't have any existing data. But I want the length to be 8. I don't want to have to go enter that every time. So this is not that important, the initial value. Now, what I've done is made this as big as I can make it on my screen and crammed as much in here as I could. Now, I could always have gone down a little bit further. See, I'm in rung 2. In rung 1, I have a rung that can set bit 15 and bit 16 to a value of 1. And those bits are right here. I'm not going to use that right now. I might use that later. And you'll see why later. Okay, so we understand what's going on here. If I turn on input 0, then it executes this bit shift right instruction, and it moves the 8 bits, this length of 8, at this location. It moves them all to the right, bit shift right. And it unloads the last bit to the right into the unload location. Now, if it's a 0, and you've already got a 0 in there, we're not going to see any change. So typically, if you're shifting a bunch of zeros, there is nothing to see. If you're shifting ones, you know, on states, then there actually is. Okay, this next rung, I put this here so you could see input 0 and input 1 together. Input 1 is right here. That's the staged bit address. So rather than looking up here, you'll see if we've got a 1 or a 0 staged to go into the shift register, because remember that wherever the first bit is in the length of 8, so if we're doing 1 through 8, then whatever value is in this memory location, when we execute, the shift register is going to take this value and move it into here. And every time you toggle input 0 on and off, whatever value's in here will go into here. But before it puts this value into this location, it will move, look down here at the bottom, it'll move element 1 into the unload bit. And of course, because the unload bit up here also shows output 0, when it puts it from element 1 into the unload, it will also show up in the output. Then once it's moved 1 to the unload, it'll move 2 to 1, 3 to 2, 4 to 3, 5 to 4, 6 to 5, 7 to 6, 8 to 7, and then it will move the staged bit address into position 8. And of course, this is happening in microseconds, so if you pictured the ping pong balls all getting moved at once, they really don't move at once. You push on 1, and then it starts flexing the 1 in position 8, which goes against the 1 in 7, and so forth. So there is a slight delay. Let's keep on going here. Now, I have 16 bits, or 16 elements of an array. It's called Station 1, element 1 through 16. I did that so I had some range to play in. In other words, if I only had 8 through 1 and I have a length of 8, then I've got nowhere to go with the offset. So I can't use the offset to demonstrate anything. So I'm going to download this and I'll be right back. Okay, we're downloaded and online. The two instructions, bit shift left and bit shift right. Well, which is your right and which is your left? Well, it depends on how you're looking at the memory location. Typically, when you look at memory locations, if you're looking at a 16-bit integer, 16 bits in a row, that the least significant bit's going to be to the right and the most significant to the left. Now, when I added my, if you want to call it HMI rungs here, in other words, I'm showing true if on instructions, and I'm looking at bit or element 1 through 8 and 9 through 16. I could have had 1 up here and 16 down here, and then they would have been going in the wrong direction if you're thinking to the right or the left. This way they're going towards the least significant, which is towards the right. So this way is right, going from 8, 7, 6, so forth. That's moving to the right. Left would be going from 1 to 2 to 3 to 4, as you see it on the screen. When you look at the actual bits or the elements in the array, it's up and down. If we go to global variables and go to
station 1, see they're displayed up and down. So left and right, up and down, it's relative to what you're thinking. But normally when you look at the bits in a memory array, the lowest memory location is on the bottom of the stack, and the least significant bit is all the way to the right. And so that's what we did here. Now these are not bits of a word, even though version 13 allows you to create integers and double integers and be able to directly address them to the bit level. If you try to apply a shift instruction, you're not going to get the desired results. You have to use an array. So that's what we're doing here. You can think of this as 16 bits in a row, 16 bits in a row as in a integer type. And when you look at it on your screen in memory, you always see the least significant bit all the way to the right and the most significant all the way to the left. And so that's what we're doing here. And that's what they mean by shift right and shift left. Now let's execute this bit shift instruction in the standard fashion. These two bits right here are not part of the array. The array is station 1, element 1 down here in the bottom. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so forth to 16. Those 16 memory location is the array. If you want to call it a register, it's not really a register, but it is 16 consecutive bits that we are shifting something to the right, which is towards the least significant. Okay, the staged bit address, input 1, right here, see bit address, input 1, that is not part of the array. That could be any bit, any place else in memory, and when we execute this bit shift right, it's going to load the state of that bit address into the first position after it shifts them all to the right. So down at the bottom here, we also are showing the .unload bit and then the output, and we're calling that unload location because see, the unload bit here in our instruction is then going to output 0. So let's bring up our simulator, and I'm going to have it right here simply because I'm not blocking anything. As you can see, there's nothing there to block, and there's not enough space left on the screen to show it, and I wanted this as large as possible on your screen. So right now, if I toggle input 0 right here, now what you don't see is we have buffered inputs, and we're taking the actual hardware input 0 and we're basically translating it or transferring it to IN00. So this is called buffering your I/O, and if you don't know what that is, typically do that if you don't want to be concerned about the hardware changing state in the middle of the scan. So it's become a pretty common practice. I like it because I would rather type in IN00 than underscore IO underscore EM underscore DI underscore 00. So IN00 through IN09 is exactly the same as the actual hardware inputs. And we did the same thing with hardware outputs. So we are, in our code, we're writing to output or OUT 00, 1, 2, and 3. And then in this program file, they're being transferred over to the real hardware outputs. Okay, back to our shift register, bring our simulator back up. And if I click on 0 now, it's going to shift to the right a length of 8 bits, 8 through 1, and it's going to first it's going to shift 1 out to the unload, and then 2 to 1, 3 to 2, and so forth, and then it'll take the stage bit address, input 1, whatever state that is, right now it's a 0, and it'll shift it into there. So I'm going to turn on input 0, and you can see that the done bit came on for the bit shift register, and then I'm going to turn it back off. So that shifting took place. Well, you're not going to see anything because it's all zeros. Input 1 was off, and we shifted a brand new 0 in on top of this 0. Well, there's no real value to that other than you could say that we did shift them, and if there was anything to shift that was going to affect anything, it would have happened. Well, let's turn on input 1, okay? And notice that this now says true, right here, input 1, true, bit address. So we have a 1 or a non-staged ready to go into the most significant bit of our length of 8. So I'm going to toggle 0 on. You see input 0 comes on and then back off. And if you look down here in our, I'm calling it HMI, Human Machine Interface. These are just rungs with trueifons examining bits in memory so you can see what's going on instead of going to the global variables or your local variables to look to see if it changed state. So we loaded the value from input 1, the stage bit address right here, see true, and this, none of this down here controls anything. This is just for our viewing pleasure. It's right here that matters, that we execute, we got a bit address, we got a source, offset, length, etc. Okay, so let's turn 1 back off. So we have a 0 stage now, okay? Now, if we are going to put this value, which is 0, into this bit, if we don't move this one first to 7 and so forth, in order not to wipe out what's in 7, we would have had to have moved it to 6 before we move 8 to 7. You get the idea. So I'm going to toggle the execute back on. You see it's done, back off, and you see it moved all 8 of these bits, and this 0 right here that was there went to the unload. Well, you're not going to see anything because it's hard to tell the difference between a 1 0 and another. They're all the same. So to prove that, I'm going to toggle this on again, execute. See, it moved down here. It moved from 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1. And on the next one, we would expect to load input 1 into here. We've been loading zeros in here all this time, every time we toggle this on or off. So just to make that look a little more tidy, I'm going to turn on input 1 so you can see that something comes into 8 when something goes from 1 to the unload. So we'll toggle 0 on and off. And it happens when the execute goes on, not when it goes off. So you can see now that the value that was in this element, it didn't go off into bit space. It actually is in that memory location, BSR_1.unload. But it's also in OUT00 and in the output. If we go to the buffered outputs, you can see that that bit in memory is on and that bit in memory is on. That bit unloaded, and it's in 3 locations. The unload bit, up here you specified you wanted the unload bit to get copied to output 0, and then because we're buffering our I/O, output 0 also goes over to the actual hardware embedded output. And if I toggle, well, let me ask you a question. What value right here do we have? Station 1, element 1. What's this value? 0. So if I toggle input 0, the execute bit shift, on then off, what do you expect to happen to the unload bit location and the OUT00 location and the actual output? So let's toggle 0 on and off. And you notice that several things happen. We unloaded a 0 into the unload bit location in memory and to the output 0, which is a buffered I/O, and to this embedded. But because we had input 1 on, when we toggled input 0, we also loaded another 1 into station 8 after we moved 8 to 7. So now we have 2 1s in there. So now if I toggle 0, and I'll turn off input 1 and then start toggling input 0. you have two ones here, 8 and 7. Ask yourself, what do you expect to happen when we execute the bit shift right? Think to yourself, on and off. Now you see, now we shifted all the zeros first, but then we shifted 7 to 6, and then 8 to 7, and then we shifted this 0, the stage bit address, into 8. And this is going to do this all the way down the trail. Now, if I happen to turn on input 1 somewhere in there, shift it, turn input 1 back off, now I have another bit in here. And as I keep shifting, you see that pattern, that bit pattern of those length of 8 bits keep shifting to the right every time I go on and off with 0. Now at this point, we should see on the next toggle of input 0, next execution of the BSR, we should see this go to the unload, which should turn on output 0, and this little LED here on our simulator. And then 2 should move into 1, and then these zeros are going to shift, 3 to 2, 4 to 3, 5 to 4, and then this one's going to shift into 5, and this 0 to here, and this 0 to here. And whatever we have here is going to shift into the load position, which is the length starting at the least significant bit of the length. Now, I'm going to do something else. Notice that I have up here, I have a rung. I'm going to toggle this on and then off. Now, 6 was already on because 6 is part of our length of 8. So I externally, well, here, let me toggle this off, because remember, these 16 Booleans haven't the biggest idea of where this is all coming from. So I'm going to do this again and set those 2 bits to 1. So I had toggled this off. I just toggled both these bits on totally from some other function somewhere else in the control system. Now, I turned on 2 bits, but watch what happens now. A bunch of things are going to happen when I toggle on input 0. We know we're going to unload, we're going to shift, but this, the state of this bit, was caused by this action up here in this rung. It didn't come from the stage bit address. Okay? So let's toggle 0 here, on, then off. Notice that 6 shifted to 5, but 15 did not shift to 14. That's because 15 is outside of my length of 8. Okay, what I'm trying to demonstrate here for you is these 16 Booleans don't have the vaguest idea who's doing what. A BSR instruction, bit shift right, executes against a length of variables, in this case Booleans, and if there's more to the right or more to the left, it really doesn't matter, and I'll show you what I mean by that. So I'm going to, as long as input 1 is off and there's a 0 stage, I'll just toggle out the rest of these. There it goes to 2, 1, and out it goes. Okay, so none of these except for 15 are on. And 15's on because we turned it on up here, up in this upper rung. We set it, in other words, latched it on, and that rung is false. So if this gets turned off, this rung up here won't turn it back on unless that external influence executes again. Here's what I wanted to show you. I'm going to go in and change the offset. Right now, we're going 1 through 8. I'm going to change it to the offset to 8. Well, we'll change it to 7 first. So I'm going to the offset here, and this is the reason that I made these variables so I could do this online. Otherwise, you wouldn't be able to do this online. So I now have an offset of 7. So where would you expect the first one to pop up? We got to turn this guy on first, input 1. Notice we got a stage of 1 so we can see something happening. Now let's toggle our execute. And look where it came on, bit 14. In other words, it was 8, but then we moved 7, which would be 1, 2, 3, 4, 5, 6. So actually 1, 2, 3, 4, 5, 6, 7. So now it's element 14 that's getting loaded with the value of the bit address instead of 8, because we have an offset of 7. Now if I'd made that offset, so now I made the offset 8. So let's execute a bit shift, and where would you expect that to show up? We have an offset of 8 and a length of 8, and we've got 16 elements. So let's execute this one. But notice what happened. It loaded one into 16 after it shifted all of these. And keep in mind that because we have a length of 8, we're not unloading all the way down here at the least significant bit. So let's toggle these through. You think this in advance. Where do you think that this is going to unload from? 10, 9, 8, 7, where do you think? So I'm going to turn off input 1. I'm going to start toggling. Okay, the leading edge is moving from 13 to 12, 12 to 11, 11 to 10, 11 to 9, still there. Let's see when the unload comes on. Okay, the unload came on when we shifted 9. 9 didn't shift to 8. Okay, 9 shifted out. We unloaded the state of that element right there. We unloaded it into this bit down here. It didn't go from 9 to 8. So you see that you can have your length effectively anywhere in between the least significant and the most significant element of your array. But here's what you can't do. You cannot have an offset that pushes your length higher than the most significant element. In other words, if you make an offset so you're starting here on 13 and going 8 this way, you don't have 8 that way. You can't do that. That's the same thing with the bit shift left. You know, they're shifting to the left, and you can't have an offset and a length that don't fit inside of your elements. Now, typically we work with, I usually create an array of 100 elements, just so I have something to play with. But your load and unload have to fit within that space. Okay, that's enough of the bit shift right.
In our last discussion, we were talking about the bit shift left instruction. And a bit shift instruction shifts all the bits in consideration to the left or to the right. And the bits in some platforms can be bits in a word, meaning that you could take a single double integer, 32 bits, and shift all the bits or groups of the bits to the left or to the right. That's in RSLogix 5000, Studio 5000, and RSLogix 500 with MicroLogix Slick 500s. But with the Micro 800, it's considerably different. It's the same idea of shifting bits, but you have some restrictions as far as where you can shift the bits or in what data types. So what we did is we created an array, a 100 element array of Boolean. Now, Boolean, those are bits. Unfortunately, a Boolean data type uses more than that amount of memory. In the 5000 platform, and of course the 500 you have no Boolean data types, but in 5000, a Boolean data type uses 1 bit of the native data type, double integer. So every time you create a Boolean data type, you are using 132-bit word. Now in Micro 800, you don't really have the opportunity to shift bits around in a data type like a dent or an integer or an unsigned integer, single integer. you don't have that opportunity. So we created an array of 100 bits, Boolean data types, and we call it sequence SEQ bits, sequence bits 1 through 100. And on the screen here, you see we have 1 through 100. Now, because we're working with a length of 8, in other words, we want to shift 8 bits, we're actually shifting sequence bits 1 through 8. And the way I've got this drawn, you might think that when the cylinder pushes those ping pong balls, that it's going to push whatever is in 8 into 9. Now, if we had a length of 9, that would be true, but we have a length of 8. So really what happens is when we push on this, if you want to call it stack or row of ping pong balls to the left, that whatever's in number 8 is going to drop into a pocket that is the unload address. Now, when I say address, I mean memory location. It's a Boolean memory location. We have two other memory locations involved, input 1 and input 0. Input 0 is the execution of the shift, the bit shift to the left. Input 1 is the value that we want to place into the least significant bit or the least significant element of the array, which would be sequence bits 1. So input 1 determines the state of the bit that we want to push into the first position, a 0 or a 1, an on or an off. So input 1 is the state of the bit that we're going to load. Input 0 is the execute. So every time we turn on input 0, that cylinder pushes all the ping pong balls to the left. When we turn it off, it retracts. And whatever you have, whatever position you have input 1 in, that's going to determine whether you have a white ping pong ball or a black ping pong ball loaded up in that little yellow square. So when you execute input 0 again, it's going to push that into position 1. And of course, when it does that, it's going to push all 8 ping pong balls, white or black, and whatever's in 8 is going to drop into the unload address. Drawn a little bit better, meaning I eliminated 9 through 100 because they're not in play. So this looks a little clearer than the other diagram. Now the other diagram is correct. It's just that position number 9 is not involved in this process. But because of the way this thing is drawn mechanically, you see that 8 gets pushed through 9 as it drops into the unload address. So this is a little bit clearer drawing. So where would you use something like this? Okay, let's take a conveyor. Okay, we have 2 conveyors here, and the way I have it drawn, the objects come in on the gravity conveyor, roller conveyor. You know, it's at a slight tilt or downgrade, if that's what you want to call it, and it rolls down the rollers up against the leading edge of one conveyor. Now, if one conveyor is on, as soon as it hits the edge, it's going to get pulled onto one conveyor. And we'll just say they're cartons, cardboard or corrugated cartons with product in them. So the carton gets pulled onto one conveyor, and within just a short period of time, it's going to break the optical path of 2PE. When it does that, the PLC is going to get a object presence at that location on the conveyor. In other words, 2PE is assigned to the entrance of the conveyor. And depending on the speed of the conveyor and the length of the carton, 2PE's optical path will stay interrupted until the carton clears the optical path. And then if it keeps on traveling, it'll eventually get down to 3PE and then go off of one conveyor onto 2 conveyor, and then repeating that on 4PE. So let's just consider one carton getting pulled onto one conveyor and breaking the beam at 1PE. So now we're going to add a device to our conveyor. It's called a pulse generator. And technically you could say it's an encoder, and it has wheels that ride on the conveyor belt. So whatever the pulse rate is of that encoder, for every inch that the conveyor travels, it's going to put out X number of pulses. Now, this particular pulse generator is not going to have a high number of counts per rotation like a conventional encoder. This is going to be something less. And the gear ratio, if you like ratio, between the diameter of the wheel and the diameter of the shaft is basically a ratio of how many inches the conveyor has to travel to get one full revolution on that pulse generator. So let's say that pulse generator is 100 pulses per revolution, and you have a circumference of that wheel that's 12 inches. Now, I don't know what the diameter would be to work out to 12 inches, but you get my point. So as the conveyor runs, when the conveyor has moved a distance of 12 inches, the belt surface, that pulse generator is going to have put out 100 pulses. So if we consider these two conveyors, we can basically accumulate cartons on here, and using a shift register, we could determine where the cartons are at on the conveyor based on the bit pattern. So if I go back to my register here, and I've only got 8 bits shown here, and if that pulse generator puts out 100 pulses per 12 inches, and the conveyor is 8 foot long, that's 96 inches for that conveyor. And we have a length, our actual array is 1 through 100. So we have 100 inches of virtual conveyor. So in other words, if we take, 96. We have 96 inches of conveyor, and we have 100 bits, 100 booleans. So we'll just say that we'll designate 96 of those, and each one represents 1 inch on the conveyor. Now, you could start at 1 and unload at when it reaches, in other words, use a length of 96. And where that 96 start depends on the offset. Remember that these bit shift registers or bit shift instructions have an offset. And you can use the offset to accomplish which 96 bits you want to shift. This is not in the manual. This is something that we discussed, though, as a possible application for a bit shift instruction. Now, in this case, we're doing bit shift left. You could use the bit shift right. It just depends on what your view of the conveyor is, because we're just shifting bits along a virtual conveyor. So this particular virtual conveyor, it's not 96 inches or 8 feet like the one that we discussed. What I realized was when I set it up that it takes too long to sit there and wait for these positions to make it all the way to the in and out. So we reduced it down to a length of 12. So you look at the bit shift left instruction, there's a length of 12. The bit address is input 5. So input 5 is our photo eye. Right now I have input 4 on, as you can see on the simulator. The reason we added conveyor 1 running input 4 is so we could pause the conveyor. So basically you can say that input 4 turns the conveyor on and off. And now in this case, it really says the conveyor is running. So something else is turning the conveyor on and off, but I'm using conveyor 1 running to initiate or to control the pulse generator. Now remember, the pulse generator was an encoder type device that had wheels on it, and it ran against the conveyor belt. So whenever the conveyor belt was moving, the wheels were rotating and generating a pulse. And I'm using a 1 second pulse, half a second on, half a second off. because if I run it any faster, then the bits don't update in our little virtual HMI here. So this is where we're going to watch the objects move across the conveyor. So remember, we have a length of 12 down here. So that means that the bits are going to get pushed into sequence bits 1, and when they get pushed out of 12, they go into the O zone. They don't use 13, 14, 15, 16, and all the way up to 100. Remember, sequence bits, that's an array of 100 elements, 1 through 100. We're only using a piece or a section of that array of Boolean type data types in memory. So let's pop on input 5. That's the photo eye. So I turn it on and then I turn it back off. And you notice now I have a Boolean value that's seeing the shifting bit, and when we leave 12, it's gone. I mean, that's as simple as it gets. Now, I realize 12 would only be 12 inches if it's 1 inch per pulse. So let's leave it on for a couple pulses. We got 2. So you see 2 marching across there. If you see 3, it's just a lack of screen update time. So this is really pretty simple. Now this keeps track of the position of an object on the conveyor. So if we left this 5 on for, I'm going to watch pulse generator conveyor 1 up there. When it turns on, I'm going to turn this on. 2, 3. Well, actually I left it on a little bit longer, but you see it's kind of hard to look at because you can't, sometimes it looks like 3, sometimes it looks like 4. But this gives you an idea of how you might track parts on a conveyor. Not track what it is, only that there's something there. Because remember, photo eye 2, it just sees something at that one position on the conveyor. So nothing can see what's on the conveyor, but what we're doing is we're using the pulse generator, which is motivated by the belt, the conveyor belt, and if it's accurate, then you're going to see whatever length. Now remember, because this is 1 second, that kind of limits the resolution. If you take the speed of the conveyor, and let's say that the conveyor is going really fast, an object might be in front of that photo eye longer than you imagine, simply because we're only triggering the bit shift left with the pulse generator conveyor 1 pulse once per second. So if an object there was there for, we'll see if we can outsmart this puppy. Okay, I just turned 5 on and off while the pulse generator pulse was off. So we'll go back and watch the pulse generator conveyor 1 up there. Oh, I missed it. Try that again. Anyway, I just toggled 5 on and off, and you see there's no bits here moving. Okay, so that's a good example of how you might use a bit shift instruction to determine where objects are at on a conveyor. Well, we have a few things left to tidy up yet in this lab project. We did the bit shift left. We spent all of our time so far working with the bit shift left. The only difference between the bit shift right and the bit shift left is the direction that the bits get shifted, which means the bit address is going to be different and the unload is going to be different. So if you have a length of 8, you see these are both 8, the bit address is input 1, the bit address is input 3. The difference is where that is inserted.
So just for grins, we do have a 1 in bit 3. So we'll take and watch bit 3, 4 here in input 0. That's the bit shift left. See, it shifted it to the left. Here, input 2 executes the bit shift right. So if we go to 2, watch bit 4 there. Whoops, input 2. Do that again. I was busy clicking on the wrong input over here, and I messed this up. So doing input 2, you can see it goes, it goes to your left on the screen. But remember, this is the least significant bit. So I'm going to pause and draw these different, and then I'll be right back. Notice what I did. I flipped the sequence of these around, so the least significant bit is on the right side and the most significant on the left side. And if you're looking at a word in memory, the least significant bit is normally drawn on the right side. So if you shift left, that means you're shifting from a lower significance to a higher significance. So let's go ahead and throw in some values. Input 1 is false, so we'll turn on input 1. Then we'll toggle input 0. Okay, so let's turn on input 1 here. So our bit address is true, and we'll toggle 0 on and off down here on the simulator. Now you see we have a 1 at sequence bits 1. So the least significant bit is now 1. We'll toggle it one more time so we have 2 in a row. Now let's turn off 1 and toggle this again. You see, every time we toggle it, it moves it to the left. If we go down to our bit shift right and toggle input 2, see, it moves it back to the right. To the left, 2, 3, 4, 5. To the right, 3, 4. So the only difference between the bit shift left and the bit shift right is that not just the direction that it shifts the bits, but where it loads and unloads. So our bit shift right, output 1 is our unload. And remember, if you unload a 0, that doesn't turn on output 1. So let's shift our bit shift right one more time, and you see output 1 is on. Down here, output 1. Shift it again, output 1 is still on, shift it again, and it's off. We've shifted out all the ones. So that's simple. There's one more thing we wanted to do, and that was recirculating bits. So we've got a bit shift left here, and we're using the same bit as the bit address that we're unloading to. Now, that means that and this is a bit shift left, so we're going from 14 up. So here's our recirculating bit shift. We're going to unload to bit 1, sequence bits 1. That's also our bit address. So nothing here actually turns on any of these bits. So our bit address is tied to the unload. So we can use any method that we want to turn on any of these bits. Now you see right now, sequence bits 2 is on. I can toggle that off and toggle on any bit that I want. And I can do that with code. So picture a circle with 8 locations around the circle. So that would be dividing up 360 degrees by 8. So you would divide it by quarters, and each quarter by 2. So you have 8 positions in a circle, and right now position 6 has an object on it. If I execute this bit shift left by toggling 6, moves to 7, moves to 8, and now it's going to move to 1. See, every time I toggle it, back to 8, toggle it again, and 1. So it's recirculating. And we did that by tying the unload back to the bit address. And then you can use other methods to turn these bits on and off. You can write a rung of logic that says if the photo eye is tripped and this and that and the other thing, then turn on sequence bits 3. So if you had a rotary index table with 8 stations and you did a certain function or procedure at station 4, when that logic is complete, then it would turn on that bit. And then when you rotate the table, that part now moves to from 4 to 5 and so forth. Now you can do this with bit shift right. So we could set up a bit shift right. So if you reverse the direction of the rotary index table, it would reverse the direction of the recirculating bits. If I don't explain where to get the manuals and what they are in the videos, then I get dozens of emails asking where to get the manuals. So here's a quick little ad, if you like. This MicroLogix this RS Logix 500 manual is really the culmination of quite a few years of MicroStarter Lite, MicroStarter, and RS Logix 500. RS Logix 500 will program all SLC 500s and all MicroLogix. MicroStarter and MicroStarter Lite will only program MicroLogix. The starter is not free. It's about $200. Starter Lite is free, but Starter Lite will only program the MicroLogix 1000 and 1100. Then for 5000, RS Logix 5000, Studio 5000, we have 3 volumes, Fundamental Programming, Programming Examples, which is really one manual broken into 2 volumes, and then the Advanced Discussions and Lab Projects. The software for this hardware that this programs, the least expensive license is about $1,000, just under $1,000. And the hardware is also relatively expensive. You can find used compact Logix with some I/O for in the $500 range. But the minimum license is going to be just under $1,000. For Connected Components Workbench with the Micro 800, the software is free. So you don't have to buy any hardware. Starting with version 12 of CCW, they included a simulator that works really well. And we really emphasize the simulator in all of our manuals. We also have a separate volume for PanelView 800 and PowerFlex 525. The PanelView 800 projects in this 3rd volume, they are integrated into the actual lab projects in Part 1 and Part 2. So after you do a lab project in Part 1 or Part 2, for the most part, most of the labs, you can then immediately go to the 3rd volume and do a PanelView lab that integrates with the project you did in Part 1 and or Part 2. Not all the projects in Part 1 and 2 have PanelView 800 projects that complement them. And then for PowerFlex 525, we have both projects using controllers, and also we show you how to hardwire your PowerFlex 525s with push buttons and lights. Have a good day. for the volumes that you see, the lecture discussions are complete and available for all but the part 2 of the CCW manual. Most of them are complete and currently going on YouTube free, and we don't have any done yet for the 3rd volume for the Panel View 800 or PowerFlex 525. But keep in mind, you don't need to subscribe to the videos to do the projects in these manuals. The videos are for people that would like a little bit more explanation and tutoring. Have a nice day.